Hi, folks. Now that we've learned about all of these different types of reaction, I want to just kind of make sure that we can look at a variety of different types. We've focused on each type of reaction one at a time and done a bunch of practice problems of that type, but we need to mix things up, make sure that we can identify this is a neutralization reaction, this is a decomposition reaction, this is a combustion reaction when they're all mixed together and we don't necessarily know ahead of time which kind of reaction we're looking at. So, this is a summary of all of the different reaction types we've learned about. We've learned about double replacement reactions and two types of double replacement reactions. We've learned about precipitation reactions and we've learned about acid base neutralization reactions. In a double replacement reaction, you'll always start with two compounds, both of which are aqueous, they're in solution. And then you get two compounds as your products. In a precipitation reaction, you end up getting a solid as one of your products. And in an acid base neutralization reaction, you get uh, water, liquid, as one of your products. For redox reactions, these are all kind of different types of redox reactions that we've learned about. Synthesis reactions, they don't have to be redox reactions, but in Chem 1, when we're asking you to predict products, they are because in Chem 1, we only start with elements. We always start with two elements in Chem 1 if we're asking you to predict what the products are. It is possible to have a synthesis reaction where you start with two compounds. But what makes a synthesis reaction is that you start with two reactants and you or more, and you make one compound as your product. Decomposition is the opposite of synthesis. You start with one compound and you make two or more products out of it. In Chem 1, those products will always be elements if I'm asking you to predict what the products are. However, decomposition reactions do exist where one compound breaks down into uh, two or more compounds. Single replacement reactions are always redox reactions, and this is the type of reaction we spend the most time on in terms of redox reactions. But also combustion reactions are redox reactions. Um, do watch when you're looking at combustion that you don't confuse it with single replacement reactions. They both start with one compound and one element. The difference is that in a combustion reaction, you always start with hydrocarbon as your compound and oxygen as your element. So let's do some practice problems. My recommendation is that you pause the video and see if you can do these before me, and then resume the video and check to see if you've got it right. Here I have an element and a compound that are reacting to form a compound and an element. This, by definition, is a single replacement reaction, which is a type of redox reaction. Here I have a compound and a compound reacting to form a compound. The key thing here is that I have two things becoming one thing, two reactants becoming one product. This is a synthesis reaction. It is not the type of synthesis reaction where I would ask you to predict this barium hydroxide product on your own, but you can be given an equation that is more complicated. I didn't ask you to predict the products. I just asked you to identify it as being a synthesis reaction. Here I have a compound and a compound making a compound and a compound. This format is typical of a double replacement reaction, and specifically, my double replacement reaction has an aqueous solution, and we form a solid and an aqueous solution. So this is a precipitation reaction. My next example, I have a compound plus an element makes a compound plus a compound. Compound plus an element often means single replacement reaction, but I notice that my compound here is a hydrocarbon. It's made up of hydrogens and carbons, and my element is specifically oxygen. Therefore, this is a combustion reaction. The last example here, I have a compound becoming a compound and a compound. Once again, this is perhaps not an example. This is not an example I would ask you to predict products for in Chem 1. But because I started with one reactant and formed two or more products, this is a decomposition reaction. So the key is the number of reactants for a decomposition reaction. Let's look at some examples then where we need to predict the products. In order to predict products, we first need to know what kind of reaction we're dealing with. So here, I've got lead nitrate, which is a compound, and I've got sodium hydroxide, which is a compound. When I see a compound reacting with a compound, I think of a double replacement reaction. So because this is a double replacement reaction, what I need to do is I need to split each of my compounds into its ions and then play the dating game and find a new partner for lead and a new partner for sodium. So let's do that. I have lead ions, and lead can have an ion charge of +2 or +4. But I know that nitrate ions have a charge of -1. And if I have two nitrate ions with each with a charge of -1, my lead must have had a charge of +2 in order to balance out that ion charge. So I've got in solution, this substance splits into its ions, lead with a charge of 2, nitrate with a charge of -1. Sodium ions always have a charge of +1, and hydroxide, that polyatomic ion, has a charge of -1. So if lead has separated from its partner of nitrate, uh, it needs to find a new partner, and opposites attract. So that lead has to be attracted to the hydroxide ion over here, and I need two hydroxide ions to balance out my one lead ion with a charge of +2. So my formula for lead 2 hydroxide is PbOH2. And then sodium and nitrate are left to bond together. But the charge of +1, the charge of -1, those already balance out. So I don't need more sodiums. I don't need more nitrates. Please remember to always write the positive charge first. So I will write NaNO3. And then I need to balance this chemical equation. I need two NaNO3s to balance out the nitrate ions. And I need two NaOH to provide the two sodiums and the two hydroxides that you see in the lead 2 hydroxide. Now that I've done this chemical reaction, this would, or produced products and balanced, this substance would be aqueous in solution. This substance would be aqueous in solution. But lead hydroxide would be a solid because most hydroxides are not soluble. And sodium nitrate would be aqueous. So not only is this a double replacement reaction, we see that this would be a precipitation reaction. The next example has an element, magnesium, reacting with silver bromide in now. If I, which is a compound. So if I had these two reacting together, I need to think about element plus compound. What type of reaction is that? That is a single replacement reaction. I should be on the lookout to see if it's a combustion reaction, but my compound is not a hydrocarbon and my element is not oxygen. So it is a single replacement reaction. And the best way to think about a single replacement reaction is to think about what the charge on my element would become Magnesium with a charge of 0 would become magnesium with a charge of positive 2. And also split my compound up into its component ions. Silver with a charge of positive 1. Even though it's in the dip in the periodic table, silver always has a charge of positive 1. And the bromide ion with a charge of negative 1. So at this point, I'm looking to see who magnesium would be attracted to here. Magnesium would be attracted to the bromine because opposite charges attract. But I would need 2 bromide ions to balance out the 1 magnesium. So my formula here would be MgBr2. And silver is left alone, so silver is going to be the element at the end of the reaction. With single replacement reactions, we've learned to answer the question, will the reaction actually occur? So you look at the reactivity series and you see how the two metals that are competing to be with the bromide ion, how they compare to each other. Magnesium is higher up in the reactivity series than silver is, and therefore magnesium is more likely to be found in compounds, and silver is more likely to be found alone. So in this example, silver is likely to end up alone, and magnesium is likely to end up in the compound. Example 8. We start with silver oxide. Silver oxide is just one substance as my reactant. It is a compound. So if you start with a compound as your reactant, this should be a decomposition reaction. With decomposition reactions, if I'm asking you to predict products in the Chem1 level, I'm just going to have you separate this compound into its elements. So we would create silver element and the oxygen element, remembering that oxygen is diatomic, so it does need to have a subscript of 2. In order to make this balanced, I have to write a 2 in front of the silver oxide, but that means I have 4 silver atoms with my 1 molecule of oxygen. Next example, the fluorine is reacting with iron chloride, which is a compound. If you have an element reacting with a compound, this is going to be a single replacement reaction, so long as your compound is not a hydrocarbon. It is not. And your element is not oxygen. It is not. So once again, I'm going to think about my element and what its charge would be if it became an ion. So fluoride forms ions with a charge of -1. Iron, in this example, has a charge of +3. And chloride has a charge of -1. Incidentally, that's how I know iron has a charge of +3, because iron can have multiple possible ion charges, +2 or +3. But because there were 3 chloride ions, each with a charge of -1, I knew that iron must have a charge of +3. I'm now going to play matchmaker and find out who iron would be attracted to. In this example, it would be attracted to the positive charge on iron. So if iron has a charge of +3, then, and the positive iron, the positive ion needs to be written first, I would have FeF3. And the chlorine would be left alone as an element. Remember, chlorine is one of those diatomic elements, so I need to write a subscript 2 with my chlorine. And then in order to balance this, I need 3 fluorines with 2 iron 3 fluorides, so that I have 6 fluorines on both sides. But now I've got 2 irons, so I'm going to need to write a 2 in front of the iron 3 chloride to balance the ions. That also gives me 6 chlorines. 2 times 3 is 6 for my chlorine. So I need to write a 3 out front here. We should also consider whether this reaction would occur. So if you think about the reactivity series, just think about group 17 on your periodic table. Chlorine is high in the group and chlorine is lower down in the group. So chlorine is more likely to be in a compound and chlorine is more likely to be alone. And that is in fact what we see here. So yes, this chemical reaction does happen. Example 10. In example 10, we have an element, potassium, reacting with another element, iodine. If you have an example where two elements are reacting together, that will be a synthesis reaction. And I need to come up with the compound that combines potassium and iodine. Potassium is most likely to form ions with a charge of +1, and iodine is most likely to form ions with a charge of -1. And those ion charges balance out. So my final product would be potassium iodide. In order to balance this, to get 2 iodines on the right-hand side, I need a 2 coefficient in front of potassium iodide, and I also need a 2 coefficient in front of the potassium. Example 11. Here I have C6H12, which is a compound, and O2, which is an element. These are, if I've got a compound plus an element, I might be thinking about a single replacement reaction. However, this is combustion because my compound is hydrocarbon with hydrogens and carbons, and my element is oxygen. So this is a combustion reaction, which means automatically my products will be carbon dioxide and water, because oxygen is going to react with the carbons and oxygen is going to react with the hydrogens. So to balance this, I need to think about my carbons, my hydrogens, and my oxygens. I need 6 carbon dioxides on the right side, so that I have 6 carbons on each side. I need 6 waters on the right-hand side so that I have 12 hydrogens to match the 12 hydrogens that you see on the left. But now the question is, how do I get the right number of oxygens on the left side to match the 6 times 2 is 12 oxygens plus 6 times 1 is 6. So I have 18 total oxygens on the right-hand side. The way to get 18 oxygens on the left-hand side is to write a 9 in front of the oxygen molecule. So 9 times 2 is 18, and this is now a balanced chemical equation. I hope this helps.